Ladies and gentlemen, this class recording has started, hopefully with audio. So, over the past couple of days, we have been discussing this outline that I gave to you on Tuesday that said location of the electrons in the quantum mechanical model. And we discussed the idea that on your outline, right, location just says location, but on my presentation, location has quotation marks, right, because like we discussed, we don't really know where, right? We're talking about probabilities and likely spots where electrons are to be. We'll talk about how do we know whether electrons are actually there or not a little bit more on Friday, but today we're sort of laying the groundwork for that, all right? Yesterday, we talked a little bit more about this on Tuesday, but talked more about it yesterday, that these orbitals that exist, these likely places where electrons could exist, we refer to as orbitals, right? Areas of high probability. That doesn't necessarily mean that electrons are there, but there is a good chance that electrons are there. We refer to these areas as orbitals. And we introduced a little bit on Tuesday, not so much yesterday because we were drawing our picture, but Tuesday we talked about the idea of quantum numbers. How do we distinguish all of these orbitals from each other? All right? And we discussed the idea that there are 4 quantum numbers. We represent those 4 quantum numbers with N, L, M, and S, and those each stand for something that makes each orbital that shows up on that drawing that we drew yesterday has a unique combination of these 4 things that distinguishes it from all of the other orbitals that we drew. Okay? And so, yesterday, we started in on drawing the picture. And our picture started like this, right? XY axis, nucleus at the middle. And the first thing we drew was a small little spherical shape around it, right? We said that was the first orbital. That's the first area where we are likely to find electrons. But we also talked about the idea that will we find a lot of electrons in that space? Not really, right? Because why? Right. So we said, Sean, that this whole picture that we made was really a combination of 2 factors. Do we remember the 2 factors that determine where orbitals show up around the nucleus? Okay. Anybody else? What are the 2 things that we said that contribute to where all these orbitals eventually or ultimately show up? Back good. Nucleus attracts electrons because nucleus is positive and electrons are negative, but and electrons repelling each other because they're all negative. We said it's kind of, a dance of how close can these electrons get to the nucleus while still being as far away as they can from all the other electrons. And that contributes to what shape these orbitals are, how they get set up around the nucleus, and how they get set up relative to each other. Okay? So, the next one that showed up also looked like a sphere, right? But it was a different color. And we said that every time we change colors, that changes a principal energy level, right? That we're moving one layer out from the nucleus. But as we start getting farther and farther away from the nucleus, these electrons have more space to spread out. So we will find more electrons within the second principal energy level. It's farther away from the nucleus, yes, but there's more space for them to spread out. So that will contribute then to there being more and more places. But even though it is a bigger space, we don't necessarily find those electrons all nice and evenly distributed. There's certain areas that allow them to fit into other spaces better than some others fit certain spaces better than other places because of the contribution of how close can they get to the nucleus without getting too close to each other, right? And then we added the next layer on, right? Another sphere, okay? And then we added those petals, right, that sort of show up on the outside of the sphere, right? But once we got to the third level, right, now we added a new combination, right? We added like this thing, this other area that we referred to as the butterfly, or the other class did, and I thought that was pretty okay, so I kind of used it for you guys as well, okay? But then, again, now we have more possibilities for where these electrons could be because more space. There's more area available for them to have access to the nucleus while still sort of spreading out from each other. And then, right, on top of that whole level, right, now we add green onto it, right? And then green had petals as well, right? I know we drew this all yesterday, so that's why so okay. And then, right, even though I didn't show you this yesterday, right, now the butterfly shows up on green as well as it did with blue, right? So we see a pattern developing here as far as what shapes do these orbitals have, what shapes show up first, what show up second, what show up third, and then we go from there. Okay? All right. It's okay with the picture at this point. So here's what I want to do today. All right, here's what I want to do today. I want to, now that we've drawn this picture, I want to go through your outline and start identifying the terms and how we represent those terms in relation to this picture. We will come back, we will reference the picture often, okay? And then hopefully by the end, we will start applying the terms and the symbols that we use to represent those terms to this picture. And hopefully at that point, we'll all come together in a nice synergistic fashion, and it will all make sense, and you'll all be like complete experts on quantum numbers. So that's my goal, have make complete expert on quantum numbers in the next 35 years. So, it's lofty, but I think we can do it. So. All right. So as we talked about, there are each orbital, each one of these spaces that we drew on this picture, the different colors, the different shapes, the different levels, right? They all have a unique set of 4 numbers that distinguishes that shape from every other shape that we drew, okay? From the first yellow sphere that shows up way down underneath all of this stuff to the green butterfly, which is the last one that we drew. They all have a unique set of 4 numbers that distinguishes it from everybody else. Just like a house on a street in a development, okay? Sometimes houses look very similar and they're close to each other and stuff like that, but there is an address that distinguishes that house from every other house in the development, in the city, whatever it might be. Okay? Good there? And that's where we're ultimately headed with this idea of the quantum numbers. What is that address that distinguishes that house from all the other houses? Okay? So, the first number that we have to worry about is the principal quantum number. And I think we got to this a little bit on Tuesday. Is that right? Okay. So the principal quantum number. First, we use the lowercase letter n to represent that principal quantum number. But more importantly, it represents or describes for us the main energy level where the electron is found. Referencing this picture, which you guys have not in the outline that we're currently looking at, I probably should give that to you, but in the outline on Monday that we filled in, the very last page down at the bottom showed that progression of the atomic models of the different scientists. This was the last one. This is Schrodinger's atomic model. So, notice, big dark band very close here to the nucleus, kind of almost looks like a circle. Then there's a lighter band that shows up. Then there's another dark ring farther out from the nucleus and separate from the initial dark area right in the middle. Then another lighter green band right through here, and then another darker band. Not quite as dark as the first two, but still darker than the other areas around. Also, remember, right, there are some dots that show up in between those bands. They're not completely exclusive from one another, but more probability here than in the light green section. Okay? Each one of these dark areas represents a principal energy level. On our drawing that we made yesterday, those are all represented by the different colors. Every time we changed a color, we moved from this area to then this area to then this area. So a color change represents a principal energy level. Okay? Orbitals that are closer to the nucleus have electrons with lower energy. That still holds true. So on our drawing that we made yesterday, electrons that show up in, say, right, these red orbitals are going to have less energy than electrons that show up in these green orbitals, because these green orbitals are farther away from the nucleus. Orbitals that are farther away from the nucleus, higher principal energy levels, electrons with more energy. Good there. Okay. All right, now let's start getting into all the different shapes that show up. What we find out is that within each principal energy level, right, every time we change colors, there are certain areas that show greater electron density than other areas. Okay? Just because they're the same principal energy level doesn't necessarily mean that it gets all that the electrons get all nice and evenly distributed around the nucleus, because they don't. Okay? These levels within the principal energy level are called sub-levels. All right? Those sub-levels are orbitals, right? All of these things are orbitals, right? They are areas that have high probability of finding electrons, but because of the dance between the attraction to the nucleus and the repulsion by all the other electrons, certain shapes start showing up within a pattern. Okay? The first sublevel in each principal energy level is called the S sublevel. Every time we changed color, what was the first shape that showed up? A circle. Technically, it's not a circle, it's actually a sphere, okay? But that sphere represents the first sub-level within each principal energy level. Okay? The very first one that we did, right? The very first shape that showed up on this picture is a yellow sphere, right? That is the first principal energy level, but it's also the first sub-level. Okay? When we moved out from yellow to red, first thing we drew was a sphere, because that's the first sub-level within red. Okay? Every time we changed a color after that, we start with a sphere. Every principal energy level has a spherical sublevel. Okay? Good with that. We call that sublevel the S sublevel. Oh, okay. These are all S sublevels. Okay? The first principal energy level has an S sublevel. The second principal energy level has an S sublevel. The third principal energy level has an S sublevel. Okay? But Julia, I think you asked yesterday, right? Like I said, these are like hollow spheres, right? Or we talked about like the nesting dolls, right? So they completely enclose the previous one, right? They don't necessarily touch, right? There's some space, but they do all enclose everything that's inside of it. Okay? Every principal energy level starts with a sphere, an S sublevel. Okay? Good there. But when we got to the second principal energy level, right? Red on our drawing, it started with the sphere, but then we added these petals. Okay? These petals are the second sublevel within the principal energy level. Okay? Good so far? Okay. They're always the same shape. They're always in this figure 8 sort of shape, right? Or we kind of referred to it as petals yesterday. Okay? We kind of talked about yesterday that these two go together. This is one orbital within the second sublevel. There are actually 3 orbitals. Okay? Remember we said there's one that runs left and right, there's one that runs up and down, and there's one that runs front to back. Okay? Those 3 together make up the second sublevel that we call the P sublevel. Okay? I think this might have been where we left off yesterday, or on Tuesday maybe. Okay? So, down at the bottom, sorry, let's go back up to here. Down at the bottom of page 1 of your outline, okay, Roman numeral 4, energy sublevels, right? So within, or A, it says within each principal energy level, areas of greater electron density exist. We call those areas sublevels, okay? So it says the first sublevel in each principal energy level is labeled as the S sublevel. It's the sphere. All principal energy levels have an S sublevel. We assign that value L equals 0, and we'll talk about that here as it comes together, all together when we talk about all the sublevels here in a second. Okay? So that's our first sublevel. They all look like this. But then the second sublevel is labeled P. On our picture that we drew yesterday, those are the petals. Every time we changed color, sphere first, petals second, except with the yellow, right? The first principal energy level doesn't have a P sublevel. It's too small. But each principal energy level from 2 on up, red, then blue, then green, they all have a P sublevel. We assign a value of L equals 1 to the P sublevel, okay? Regardless of which principal energy level it's in, okay? Okay. P orbitals look like this. And that petal is sort of figure 80 kind of shape. Okay? P stands for petals. That was completely coincidental. The last class, the first class started calling them petals, and I didn't even think about it at the time. But when I put it up here, I was like, oh, that works out nicely, doesn't it? So, okay? That was completely coincidental, but hopefully beneficial. Okay? All right. This is one p level sublevel orbital. These, okay, don't write anything down just yet. You'll see what we'll put this together all here in a second down at the bottom of this page. But these are three individual p sublevel orbitals. One that runs side to side, one that runs up and down, and one that runs front to back. Each one of those individually is a p sublevel orbital. Put all three of them together, and you have the p sublevel. Okay? Yes, no, maybe. Good so far? No? Okay. We'll see. At the end of class today, we'll start actually putting numbers on this, and hopefully that will make a little bit more sense. Okay? All right. We'll get there. Don't worry. So that's the P sublevel, the petals. Okay? The next sublevel that shows up is called the D sublevel. These were the butterfly-shaped one that showed up first in blue, but then also showed up in green. D sublevels don't start until we get to the third principal energy level. Remember, as we move farther out, there is more room where electrons can find a space where they can be close to the nucleus, or as close as they can, while still being repelled by all the other electrons. Okay? There is a fourth sublevel called the F sublevel. I didn't draw that for you because it's pretty complex to draw. But know that there is a fourth sublevel. However, if S, the first sublevel, starts in the first principal energy level, and P, the second sublevel, starts in the second principal energy level, and D, the third sublevel, starts in the third principal energy level, when do you think F's start? Follow the pattern, everybody. If F orbitals don't start showing, F sublevel doesn't start showing up until we get to the fourth principal energy level. We're talking about some pretty big atoms at that point in time. Okay? So these don't show up a whole lot in the ones that we're going to deal with. Okay?
What kind of atoms would they show up?
I mean, we're talking like, actually, Sean, do you have a picture of the periodic table in your head?
Yeah.
Okay? You know, like it has like the two big towers like on the two sides,
Yeah.
right? Short kind of in the middle, and then there's those two rows down at the bottom. The two rows down at the bottom. That's when we start getting into F. Plutonium, uranium, those kind of, yeah. I mean, we're talking about some really big atoms at that point in time, right? Because, right. Because remember, right, each one of these things that we drew, right, going up to here, okay, these all represent places where electrons could exist, right? So there's lots of places where electrons can exist within atoms. Now, somebody asked before, it's actually a pretty good point here, somebody asked before, do orbitals exist if there are no electrons in them? And the answer is yes. Orbitals are spaces. They're areas where electrons could exist. Whether electrons are actually there or not depends on first how many electrons are there, right? And then what are those electrons doing? Good.
Just a quick kind of random question.
Good.
Put it on a
In theory, yes. Okay? But are there electrons in them? That's a different story. If we think of this kind of like a new development, we can build a bunch of houses in a new development. And those houses would all have addresses. But does that mean people live there? Not necessarily. Does that make sense? So these orbitals that we're drawing in this picture, these are like houses in a development. Tomorrow, we'll start talking about, do people actually live there or not? Are there electrons actually there? And that's when we start getting into orbital diagrams. We'll talk about that tomorrow. Okay? All right. So to summarize all of this, we have this chart, which I believe you guys have down at the bottom of page 2 of your outline. Is that correct? This chart shows us, first, the general shape of the different orbitals in each sublevel. Right? S orbitals are all spheres. P orbitals are all figure 8 or petal shaped. D orbitals are mostly butterfly shaped, although there's one kind of weird one over here. Okay? Now, those colors on this drawing do not relate to the colors on our picture. Okay, so don't confuse the colors on this chart with the colors in our other picture. These are just general shapes for sub-level orbitals. Okay? Yeah, d orbitals didn't copy really well, but they're, like I said, they're butterfly shaped, right? Where they have kind of 2 lobes, or actually 4 lobes, that sort of center around the middle. Okay? And as long as you have the general shape down, and then look, the F sublevel, 7 complex shapes. It's not even worth drawing. So just know that there's a bunch of lobes, a bunch of places, and that's about it. All right. Good so far. So.
For the angular momentum quantum number.
Okay. So the angular momentum quantum number. We use the letter L to represent the angular momentum quantum number. It tells us which sublevel and, consequently, the shape of each orbital. Notice, each orbital gets its own number. S orbitals all get a L, or a angular momentum quantum number equal to 0. P orbitals all get 1, D orbitals get 2, F orbitals get 3. That's the number that they are assigned. Okay? All right. Are we ready to start to apply some of this to our pictures here? I think hopefully they'll start making sense. Okay? All right. Let's go to picture, and let's zoom back in here. Okay. This is the first orbital that we drew yesterday. And I'm going to put an electron right here in that orbital. Okay? I know it's kind of a little hard to see, but I want to keep them the same color, and we'll see why in a second. Okay? All right. Remember, these orbitals are spaces where electrons can exist. And we need to, if we have an electron there, we need to describe its location to distinguish it from all the other ones. And we said that each orbital has a set of 4 quantum numbers that distinguishes it from all the other orbitals. Okay? Its own address. So, that electron that exists in this orbital, first, what is the principal energy level that this electron exists in? Yeah. Well, no. 1. Because it's the closest to the nucleus, and it's the first color, right? So therefore, this electron will have an n value equal to 1. Okay? Good there? The L value tells us about the kind of orbital that it's in. What's the shape of this orbital, Jack? It's a sphere. It's an s orbital. The part that we just filled in said that s orbitals get a value for L equal to? Nope. What's the one we just filled in? Okay? Right here. All s orbitals get an L value equal to 0. Okay? Good there. Okay. All right. Let's go here. Okay? Okay, go ahead. That S, those list of 4 quantum numbers, is not the shape of the orbital. It means something different. I know. It's the same letter, but it means something different. Okay? All right. Let's go here. There's our second electron. It exists in this red spherical orbital. It also has to have a set of 4 quantum numbers that distinguishes it from all the other orbitals that it could exist in. Jack, what shape is this orbital that this electron is in? Sphere. Meaning, what value for L should it have? 0. All spherical orbitals have an L value equal to 0. However, which principal energy level is this electron in? Go, Julie. We've jumped up from one principal energy level to the next principal energy level. Okay? Good there? If you're keen, you might be able to figure out where I'm going next. This electron that exists in the blue sphere has to have a set of 4 quantum numbers that distinguishes its orbital from all the other orbitals. Jack, what shape orbital is this one in? So what's L value? But what principal energy level are we in? Now we're in the 3rd principal energy level. While all of these electrons have the same L value because they're all in spherical orbitals, they're all in different principal energy levels, so they're different from each other. Okay? Good there. All right. Let's go here. This electron has to have a set of 4 quantum numbers that is different from all the other electrons. Okay? So, which principal energy level is this one in? What color is it? Red. We said every time we change color, that's a principal energy level, right? This electron and this electron are in the same principal energy level because they're both in red orbitals, right? So this one has an n value. Julia, what's the n value for this one going to be? 2. But what kind or what shape orbital is it in? You can go back to the chart that we just wrote down. Okay. So, what shape orbital is it in? Nope. So this is a petal-shaped orbital, right? Which we call what letter? What kind of orbital do we call that? A p orbital. your charts, what number do we get for p orbitals that are L? 1. Go ahead, Kate. That can't be. It's got to be one or the other, because if we start now, actually, hold on 1 second with that question, okay? Because we'll get to that in just a second. Okay. All right. Good with this one? Okay. I'm going to jump you up to here. What kind of an orbital is this one in? What shape? Petal shape, right? We call that what kind of an orbital? A p orbital. So what has to be the L value? This has to have an L value equal to 1. However, what principal energy level is this one in? This is in the 3rd principal energy level. Okay? Okay? What's the N value going to be for this one? What's the N value going to be? 4. But the L value, 1. Because it's still in a p orbital, it's still in a petal orbital, okay? But it's in the 4th energy level. Julia, go ahead.
So every color, we switch colors, kind of different.
That goes to a new principal energy level. Okay? Yep. Yep. Okay? All right. Try this one. Discuss with the person next to you. Go. All right, how's that? You okay with that? Okay, now, let's increase our degree of difficulty. I know. Are we okay with those? We okay with those two? All right, increased degree of difficulty, here we go. Okay? Is it different? What principal energy level is this one in? 2. What shape of an orbital is this one in? Petal, p orbital, means that L gets a value of 1. But we said what has to be true about all these different orbitals? They have to have their own address, right? Right now, these two don't have a different address, but we still got 2 numbers to go, right? Those 2 numbers are how we distinguish this one from that one, right? We'll pick this up tomorrow, and we'll go from there, okay? Cliffhanger. Homework. You're probably not ready for that just yet. Maybe a little bit, but probably not the whole thing. So it might be a better idea to wait on that till tomorrow. Okay?